everybody to the Atto Fridays. Our speaker today is Dr. Xuanyang Lai. He is the head of theory in the Chinese Academy of Sciences, Wuhan, working on strong field and attosecond physics. He has obtained his PhD from the Chinese Academy of Sciences in 2009 and has worked there since. He was a visiting scholar at UCL, University College London, from 2012 to 13, and he focuses on the theoretical study of the interaction of atoms and molecules in strong laser fields and develops models to describe the complex interaction dynamics. And this includes Wolfram mechanics. Also, he played an instrumental role in the early developments of a method we all know and love at UCL, which is the Coulomb quantum orbit strong field approximation. And his theoretical work is closely combined with experiments. And today he's going to talk about strong field physics meets quantum optics. So welcome to the Atto Fridays. Thank you for accepting the invitation, and we are ready to go. The floor is yours.
Okay, thank you. Hello, everyone. My name is Xuanyang Lai from Chinese Academy of Science. First, I thank Carter for giving me this opportunity to present our recent work about light field quantization. The title of my talk is Strong Field Atomic Physics meets Quantum Optics. Our school is in Wuhan, central China. The Yangtze River flows through the city, and Wuhan. I use the laser point. And Wuhan has a very long history. This is the famous yellow crane tower. This is a building in our school. I am in Professor Xiaojun Yu's group, the ultra-fast science group. There are three main research directions. And my work focuses on the femtosecond and the attosecond dynamics. My talk contains 4 parts: the background, our recent works, and conclusion and outlook. The interaction of atom with strong laser field can produce many nonlinear phenomena. For example, high-order harmonic generation and high-order Barber threshold ionization, and this is the non-sequential doubleization. Using this phenomena, we can have very important applications. For example, we can synthesize the attosecond laser pulse. The 2023 the Nobel Prize in Physics was awarded for attosecond pulse generation. And we can also produce the tabletop coherent XUV light. And we can also perform the real-time imaging of molecular structures. Currently, in strong field atomic physics, the laser field is described by a classical field, and the quantum effect of the light field is ignored. The reasons are that the strong laser has very high photon density, and the laser is in coherent state, which is the closest to the classical state. Like recently, with the advances in the laser technology, people can generate strong quantum lights. For example, such as the bright squeezed vacuum. A few weeks ago, Professor Maria Chakova gave a nice talk about BSV in Atto Fridays Seminar. Like combining the BSV and the coherent state, we can obtain the phase and the amplitude squeeze light. Because of the generation of a strong quantum light, so we need to bridge the strong field physics and quantum optics. In recent years, some important progress has been made in studying strong field physics and intense quantum light, such as the effect on harmonic generation and ionization, and even competent scattering. Recently, our group has also worked in this field. So in this talk, I will introduce three of these works. The first two are related to the intense quantum lights. First for ATI, second about the attosecond pulse. The last one related to vacuum quantum fluctuation or harmonic generation. Okay, the first work is for HATI in intense quantum light. Like the well-known HHG, the HATI also comes from the electron rescattering. But unlike HHG, which requires the considering the propagation effect, this HATI is a single atom response length. It can more straightforwardly identify the effect of the intense quantum light. This is the HATI spectrum. A key feature of the HATI and a key feature of this spectrum is the cutoff energy at the 10 UP, where the UP is the ponderal motive energy and defined by this equation. To study the HATI and intense quantum light, we start from fully quantum TDSE. To solve this equation, the different quantum lights are expanded as the coherent state. Like we can get the final photoelectron spectrum. It is the sum of the spectrum from the different coherent state with the weight the Q here. Here we take four kinds of lights as an example. The first one is coherent state, second Fock state, third thermal state, and this BSV state. Here are the Q distributions. For different quantum light, they have the same average laser intensities like this. Here are the simulated HATI spectra for these four lights. This here is for coherent and Fock state. This is for the thermal state, and this is for BSV state. As we can see, the cutoff energy increases greatly for thermal state and BSV state. Like how to understand the change of the cutoff energy. In order to answer this question, here we show the quasi-probability distribution listed here. As we can see, for BSV state and thermal state, the distribution is much broader than the coherent state, like this. Additionally, the ionization yield is also important and can be calculated with the ADK rate. According to ADK rate, the higher laser intensity leads to the higher ionization rate. Then we can multiply these two terms to get figure C. From this figure C, we see that for BSV state, this one, and the thermal state, the effective laser intensity for ionization becomes much higher than the coherent state. This here is coherent state. This is the thermal state, and this is the BSV state. So we can see this effective laser intensity for ionization is much higher than this coherent state. Less, the cutoff energy increases consistent with our simulation above. Now, as we know, for coherent state, we can get the cutoff energy. It is about 10 UP. So can we derive an analytical formula of the cutoff energy for the quantum light? The answer is yes. Based on the analytical Q distribution and the ATK rate, we can find the electrical field at this peak position. For here is for thermal state. This is for the BSV state, and this is for coherent state. Second, we can calculate the new UP use this equation. Here, this electrical field is for this 4 point. Third, using this new UP, we can derive the new cutoff energy like this. This is for the 4 quantum light. The first one for coherent state, we are familiar with it. This one for thermal state, and this is for BSV state. To check out our result, whether the analytical formula is right, so we compared our result with the simulations. Here, this is for coherent state, this is for focus state, and this for thermal state, and this one for BSV state. Here we change in the wavelength, and here we change in the ionization potential. Here we take the thermal state and the BSV state, for example. When we change, increase the wavelength from here to here, we can see the cutoff energy increases. Similarly for BSV state. The cutoff from the analytical formula is marked by this arrow. As we can see, the cutoff energy from the analytical formula is consistent with the simulations. Similarly, when we change the Atto ionization potential here, the cutoff energy in a simulated spectrum also increases, and the analytical result also matches by here denoted marked by the arrow, matches the simulation well. Okay, next I introduce our work on the synthesizing attosecond with intense squeezed light. We know the attosecond pulse can be synthesized using HHG. Usually, HHG has both short and long electron trajectories, leading to the random phase. The phase matching method is usually used to select a single trajectory by adjusting the atomic position relative to the laser focus. However, the phase matching method only works for parts of harmonicas. Our work shows that using the strong squeeze light, we can select only short trajectories in the whole HHG spectrum. Here are the HHG spectrum for coherent light in yellow and in squeeze light in the blue. Here are the harmonic phase For the coherent light in yellow, it is the phase is irregular. In contrast, for the squeeze light in blue, it shows a regular quadratic distributions. Furthermore, we also calculate the wavelet. This is the wavelet analysis. For coherent state, there are contributions from the short and the long trajectories. For the squeeze light, we can see only the short trajectory can be observed. So we can use the whole HHG spectrum to synthesize the attosecond pulse. And this is here for squeeze. Here's for squeeze light. After compensating the quadratic component of the phase, we obtained a short attosecond pulse, which is close to the Fourier transform limit, like something like this. However, for coherent light, no clearly short pulse can be formed. So we have a question. What does intense squeeze light select the short trajectory? To answer these questions, we calculate the phase of a long and short orbit as a function of harmonic orders. According to all the first work above, we know the squeeze line can be expanded as the superposition of a coherent light with weight, something like this. This quasi-probability distribution. Now, due to these distributions, the phase of long and short trajectories has the phase of the long and short trajectories also has a distributions, something like here. This is for short, is for long. Moreover, the distribution of the long trajectory is much broader than this short one. The reason is that the phase of the long orbit with the longer travel time tau is much more sensitive than the short trajectory. Less the distributions, the phase distributions of the long trajectory becomes much broader than this short one. Now, it is leads to that the long trajectory are suppressed due to the distractive interference. So, next, someone may ask that can our method be used to generate an isolated attosecond pulse? The answer is yes. We can use the squeezed PG pulse. First of all, I briefly introduce the PG pulse. The PG pulse contains this left and right circularly polarized pulse with a time delay. This is the final PG pulse. Here's the ellipticity as function of the time. The central region has a near zero ellipticity. So the harmonic can emit here, leading to the generation of an isolated pulse. Okay, and then this is our simulation result with the squeezed PG pulse. And the wavelet analysis shows that for the coherent light, there are contributions from the short, long trajectories. However, when we use the squeezed light, there are only the short trajectories here remains. This result is consistent with our previous finding that in a squeezed light, only a single short trajectory can be observed. Here is the HHG spectrum. Here's we can see for the squeezed light, this in blue, the spectrum becomes a very smooth line. Like by using the whole HHG spectrum, a short isolated attosecond pulse can be obtained, and its pulse width is close to the Fourier transform limit. The above two works related to the intense quantum light. Finally, I will introduce a work about the effect of the vacuum quantum fluctuation on harmonic generation. As we know, that vacuum is not empty. It is filled with vacuum quantum fluctuation, short for VQF. Using the fluctuation, vacuum fluctuation, many phenomena can be explained. For example, the Casimir effect, and this spontaneous emission, and this Raman shift. Very interestingly, people have found that the spontaneous emission can be controlled by manipulating the vacuum quantum fluctuation. Use this photonic crystal. Now, as we know, the harmonic generation also involves the electron emission like this. Like our question is the harmonic emission also affected by the vacuum quantum fluctuation, the VQF? Usually, as we know, the average magnitude of the vacuum fluctuation, something like this, doesn't change over time. To more clearly show the effect of the VQF on the harmonic generation, we use squeezed vacuum state, something like this. In this case, the vacuum fluctuation changes with the time. Currently, the squeezed vacuum state can be prepared in experiment. Okay, in theory, we start from the free quantum TDSE here. The squeezed vacuum state is here. Like we can obtain the harmonic emission amplitude, something like this. Compared to our familiar formula, besides this electrical dipole moment, there's an additional term mu. This term is called the magnitude of the VQF given here. We find that when the squeeze parameters are equals zero, like this term becomes 1. Less, this formula reduces to our familiar harmonic formula. Here are our numerical simulation results. We consider a single model squeezing. We taking the first order and the ninth order as example. We can see here when we change the squeezing parameters, the harmonic order, harmonic amplitude changes, and this for ninth order. Similarly, when we change the squeezing angles, the amplitudes also changes accordingly. So the harmonic amplitude can be controlled with the squeezing parameters and the angle of the corresponding squeezed vacuum model. Like how to understand the control of the harmonic intensity with the VQF. So we perform the wavelet analysis, and we take the first order model as an example. This red line shows like here's this red line shows the wavelet analysis. As we can see, when we change the squeezing angle, the amplitude changes accordingly. When the squeezing angle is about 1.9 pi, the initial amplitude shows significant enhancement from here is much stronger than this here. Why? To answer this result, we modified the wavelet formula because this term mu changes smoothly compared to this window function W. So we can extract this term and obtain this new formula, this term here. The first part is our formula, the transition amplitude, and this term is represent magnitude of VQF. They are marked by this black solid curve and gray dashed curve respectively. Then we find out that harmonic is enhanced. Here, why enhanced when its VQF is in phase with the harmonic emission. So we can find the emission enhanced for this squeeze angle. Our result is consistent with the Fermi golden rule. According to Fermi golden rule, the emission amplitude equals to the transition amplitude multiply the magnitude of the vacuum fluctuation. Similarly, we can also analyze the effect of the VQF on other harmonicas. Okay, let's come to the conclusion. First, we have shown how quantum light affect HATI and derive an analytical formula for the cutoff energy of the different quantum light. Second, we use the intensity squeeze light and obtain the HG spectrum with only the short only short orbit, and we also synthesize a short attosecond pulse. Third, we show the effect of the vacuum quantum fluctuation on harmonic generation, which provide a new approach to control the harmonic emission. In the future, we will further study how the photon statistical properties of the quantum light on strong field processes. In addition, we can also control the attosecond electron dynamic with the quantum light. Finally, I would like to thank my collaborators and the financial support. Thank you for your attention.
So let's thank Dr. Lai once more. If you would like to ask questions more privately, hang in there because we are finishing the streaming. So for those on YouTube, thank you so much as well for supporting our initiative, for logging in and taking the time to watch us online. For those here on Zoom as well, stay tuned and we see you in 2 weeks.